Greetings, ACT Specialist. Commander King here, and I'm back again with another mission, this time related to limiting reagent or limiting reactant problems. We've learned a lot about stoichiometry, and now we're taking a look at something slightly different. So this past Thanksgiving, I was making these things called pigs in a blanket, I guess. And I had a bag of hot dogs, I guess, or mini sausages, or whatever they were, and then I cut out some, flour. And so I cut out the flour and wrapped up the sausage, and I made a good amount of these. I made probably like 100 of these, alright? But what I soon found out is I ran out of the hot dogs, and I was left over with excess flour, okay? And so this is a good example of what happens a lot of times in chemical reactions. You have limited quantities of both, but one of them you're going to run out of first, and this we call the limiting reagent or the limiting reactant, and then the other one that we have excess of, we just call the excess reactant because we have leftovers basically, and that just kind of stays there until something else comes along that reacts with it. Okay, so limiting reagent, it's conceptually okay, but when you get into the problems, it might be a little bit more difficult. But I don't really care about limiting reagent reactions unless there's a real purpose behind it, right? So let's think about why we care. And so let's take an example. Let's say we're trying to plant a tree on a distant planet, because we are exploring space and trying to colonize different planets in the future as the Alliance chemistry team, of course. And we're trying to colonize, let's say, Titan, Saturn's moon Titan, we'll say. And let's say Titan has limited resources of H2O and CO2, which plants need to create glucose, of course. And plants need glucose to do a lot of things. Okay, so maybe Titan, different than Earth, has a restricted supply of water and CO2. Now, this is a fictitious problem, but you can think of other cases where this might be important. So in this limiting reagent problem, they're telling us, okay, we have 75.0 grams of H2O available to the tree daily, and we also have 201.0 grams of CO2 available to the tree. And it could use both of these resources to make this C6H12O6. Now, kind of like the hot dogs and the bread, or the flour, they're not exactly going to mix completely and make the exact amount of glucose that you want. They could mix in so that one is left over. I might have too much CO2, or I might have too much H2O, and if one of them runs out, then I can't produce any more glucose. So what we're trying to figure out is, okay, based on the fact that I have both of these resources, how much glucose can I make? Because with this one, I can make with 75 grams of H2O, I can make a certain amount of glucose, and with 201.0 grams of CO2, I can make a certain amount of glucose, but which one's going to run out first in the reaction? Okay, so I'm going to try to figure out, okay, how much glucose can I actually produce? What's the limiting reagent? And what if plants needed 85 grams of glucose to survive? Would this tree survive? In other words, would this tree successfully grow on a planet like Titan if these are the resources available? Again, a fictitious scenario, but not too far-fetched, I think, at least. All right. So let's think about this problem. I already set up kind of this mole table here, the Batarian box as we call it, to help us with this problem. And again, the box is just to help us guide us along. Alright, so let's see what we know. We know we have 75.0 grams of H2O. We know we have 201.0 grams of CO2, and these are my starting points here. So I know I have both of those, and I'm trying to figure out how much glucose I can produce. So I want to know, how much of this glucose can I produce? Well, again, as we said, this 75 grams can produce a certain amount, and this 201 grams can produce a certain amount. So we want to see how many moles of this we could produce from each of these, and then we're going to pick the smaller one, because that one can produce less of the C6H12O6, and that's going to limit the reaction, or limit the product that we can create. Okay, so my first thought maybe is to, okay, how can I convert from 75.0 grams to grams of C6H12O6? And I realized, I want to go here, but there's no real direct conversion from grams of a molecule to grams of another molecule. Alright, So that's troubling. The other thing that's troubling is that this equation does not look balanced. So always remember, once you write in the stuff, to balance the equation. And we've done this a lot, so I'm not going to spend too much time, but 6 to the 12 H's, 6 C's, and then I have 6 O's, 12 more O's here, 18 O's. I already have 6 here, so I need 12 more, and then 6 times 2, now 12 plus 6 is 18. All right. Okay, so let's make a plan. Let's start with the H2O. Now, again, I'm in grams, and grams isn't a great way to convert from one molecule to another, but I can get from one molecule to another if I use the coefficients. And remember, the coefficients can only be used if I'm in moles, or if I'm in atoms, or if I'm in molecules, where it says, you know, if I have 6 of these H2O molecules, I could create essentially 1 of these glucose molecules. Or if I have 6 moles of these, I could produce 1 mole of these. So that gives me a good sense. So it looks like the first thing I want to do is to try to get to moles. All right. So it looks like my plan is to get from H2O to moles of H2O. Okay. And then from moles of H2O, using my coefficients, I can likely get to how many moles of C6H12O6 I can produce. And then I can compare it with this one. I'm going to call this conversion 2. And I can then convert to moles of this as well. And then I can see which one I produce less of, and that's going to be the limiting reactant. So let's take a look. I'm going to call this 1. And so in step 1, I'm trying to convert from grams of H2O to moles of H2O. But I don't want to end up at moles of H2O. I want to go further to, looks like, moles of C6H12O6, and I'm going to stop there for now, okay, because I want to compare these 2 mole quantities. So I'm going to start with my grams here of H2O, and I want to convert to moles of H2O. So I know I'm going towards moles of H2O. That's where I want to end up, so I'm going to put that at the top, and I'm trying to cancel the grams of H2O. And I know my conversion from grams to moles, I know I need the molar mass, and that's from the periodic table because I'm going from mass to moles, right? So I'm going to take a look at my periodic table. I know I need the molar mass for H2O. H has a molar mass about 1.008, or if I want to round even more, 1.01, and O is 15.999, or about 16.00. So if I add those two, I have 2 H's. That's 2 times 1.008, or 1.01, and I add the 16 here, so I get 18.02 grams per mole is that conversion. And so let's just line that up. So I know in every mole I have 18.02 grams, so in 1 mole I have 18.02 grams of H2O. So now I've converted from grams to moles. I'm now at this step here, and now I want to convert to moles of C6H12O6. Well, I know I'm going to cancel my moles of H2O. I need to know in this many moles of H2O, how many moles of C6H12O6 do I have? And for this conversion, I want to look at my equation here because I know to create 1 of these C6H12O6 molecules, I need 6 H2O molecules. So it's in 1 mole of this, I need 6 moles of H2O, and I can calculate that, and that'll tell me the moles of C6H12O6 that I have. I'm going to pull up my handy dandy calculator. 75 divided by 18.02 and divided by 6. So it looks like that would produce 0.69 moles, but I have 1, 2, 3 sig figs, so 0.693 moles of C6H12O6. Okay, so that's from the H2O. All right, what about from the CO2? How many moles could I produce of C6H12O6 or glucose with the CO2? Well, let's take a look. Again, I'm starting with grams, but this time of CO2. I got to first convert to moles of CO2, and then from moles of CO2, I can convert with my mole ratio to moles of C6H12O6. All right, so let's take a look. I'm starting with 201.0 grams of CO2. To convert from grams to moles for CO2, I'm going to need a conversion again. So for every 1 mole of CO2 I have, Let's look at the periodic table. C12, O2, 16. So 12 plus 2 times 16, about 44, it looks like. So in 1 mole of CO2, there are 44 grams of CO2. Let's set up my conversion. I know I want to cancel my grams. I know I'm trying to get to moles. And it looks like in 1 mole of CO2, there are 44 grams of CO2. Boom, I'm at my moles. One more conversion here. I want to cancel my moles of CO2. Well, I've canceled my grams. I'm going to cancel my moles of CO2. Trying to get to moles of C6H12O6. And so in 6 moles of CO2, right here, it looks like there's only 1 mole of C6H12O6. And then I can calculate this as well. So again, with my calculator, I'm going to take 201 divided by 44, and then divide that by 6, which gets me 0.76. So 0.76, but I need 4 sig figs, it looks like. Theoretically, this was about 44.00, so 0.761 moles, it looks like. 0.761 moles of C6H12O6. And let's plug that in right here, 0.761 moles. Okay, so what is this saying? All right, what this is saying is with 75.0 grams, I can follow my line and I can produce 0.693 moles. If I have 201.0 grams, I can produce 0.761 moles. Okay, but because I have, only 75 grams of this, I can't produce the 0.761, I can only produce the lesser amount because I don't have enough of the H2O to produce this amount of C6H12O6. So basically, I'm going to make 0.693 moles of C6H12O6 because my H2O is limited. I don't have enough of it to react with all the CO2, only some of it. Okay. So I know I have 0.693 moles of C6H12O6, and I know I've only got one more step to go. Okay, I don't want the moles of this. I want to know how many grams of glucose I can produce. So I'm going to do that in one last step. We decided, okay, 0.693 moles was what I had, and I wanted to convert in one final step back up to the grams because my original question was how many grams. Okay, so in this final conversion, we'll call this step 3, I have 0.693 moles of C6H12O6. I know I need to convert from grams to mole, and I know where to get that from the periodic table because it's a molar mass. And 6 times 12 is about 72, plus the 12 here. Yeah, let's be specific. So 1.01 times 12 is 12.12, 72.00 plus the 16 times 6 is going to be 96, and so this will add up to about 180.12 grams per 1 mole. And so if I do that conversion, I know in every mole I have 180.12 grams of C6H12O6, and this is in 1 mole of C6H12O6. The moles are going to cancel out, and let's see what I'm left with. I'm left with 0.693 times 180.12, and that gives me 124 points. Well, I've only got 3 sig figs, 125 grams of C6H12O6, and this would be the amount that's produced, 125 grams. All right, so we figured out that's the amount of glucose that we can make, even though we had different amounts of these, right? I think we originally had 75.0 grams of this, and we had 201.0 grams of this one. In the end, we can only take 125 grams. Now, if you recall, it's because this was the limiting reagent, so the H2O was the limiting reagent or reactant and prevented us from creating more glucose. Okay, and then last question was, okay, if you need to produce 85 grams if each tree needs 85.0 grams of glucose to survive per day, well, this one can produce 125 grams. So it looks like this tree would be A-okay to survive on a planet like Titan, given those circumstances and data that we've collected. All right, so that's the limiting reagent problem. And hopefully this will be helpful in your future missions. Okay, thank you very much for tuning in. King out.